Okay, so retrieval roulette for today. Oh, hold on. I'm covering one of the questions. There, that's a wee bit better. So pause, get those questions answered. Thank you very much. And here's the answers to mark them. So again, pause, mark, correct, fix any mistakes, everything, all of that. Pause, get that done. Thank you. Right, so here's the answers from yesterday. So let me check. Page 197, first of all. So gravity is the force of attraction between bodies. Between objects and Earth, it is a weak force, but if the mass is very large, as with a planet or a star, the gravity can be very strong. The region where a gravitational force can be felt is often referred to as a gravitational field. I don't actually know if you had the information to answer this yesterday. Apologies. The Earth's gravitational field attracts every object on Earth. This gives an object a weight. Weight is measured in newtons and always acts towards the centre of the Earth. 2. You had to sort these out into which one was for mass and which one was for weight. So let's have a wee look here. So amount of matter is mass, measured in newtons, weight. Measured by a balance. Oh, mass. I don't think I talked about this yesterday, right? Quite often we will say, oh, stick that on the scales there or weigh that whenever we really mean to find the mass. So see, whenever we're describing practicals and things, we need to make sure we use the word balance. So you measure the mass on a balance, okay? And it is, you'll have seen us using them in school. You'll have used them in school. Do you know, like the wee top pan balance that you set the stuff on and it tells you how many grams it is? Balance rather than scales. Not a force is mass, and measured by a spring balance is weight. Caused by the pull of gravity, weight. Same everywhere in the universe, mass. Measured in kilograms, mass, and is lower on the moon than on Earth, weight. Right, over onto 197 then. So a bag of flour weighs 1 kilogram. What's wrong with this? Weight isn't measured in kilograms. So rewrite it so that it's accurate. A bag of flour has a mass of 1 kilogram. Or if you had rewritten it like weight wise, you would say a bag of flour has a weight of, it would be 10 newtons. C was the table. So there's our values there. To go from grams to kilograms, divide by 1,000. And then to go from mass to weight, you're going to be using that W equals mg equation. So all of these numbers you'll be multiplying by 10 to get those. So pause, get that marked for me. Right, 4 and 5 then. So in these ones you were given different masses, you were told it was on Earth and you had to find the weight. So hopefully you have done your working out the same as me. So weight equals mass times gravity for them all. Substitute in my numbers. There's my answers. Mark yours. And then D, E and F, you were given the weight and you had to find the mass. So we had to rearrange our equation. If we make mass be the subject, we get mass equals weight over gravity. So for the first one, the weight was 30, gravity's 10, so it's 3 kilograms. Same working out for the rest. So 15 kilograms and then 45 kilograms. 5 was the same idea, only this time it was on the moon, so gravity wasn't 10. So you can see here all my working out. So W equals mg for A, B and C. Substituted in for the mass, and gravity is 1.6 in all these ones. So 8, 16 and 4. And then D, E and F, same as up above, you had to rearrange and find the mass. So substitute in for the weight, divide by gravity, and you get that. So 10, 50, 600. Okay, let's move on to today's stuff. Right, so turn over to 199 for me, please. We're going to be looking at free fall and what it actually means. Basically, we mean free. Let me start that sentence again. Basically, whenever we say something is in free fall, we mean that the only force acting on it is its weight. So the only force acting on it is due to gravity. I really try and avoid saying the only force acting on it is gravity, because technically, like, gravity has the units newtons per kilogram. They're not the units of force. The units of force are newtons. So if something is in free fall, that means the only force acting on it is its weight, or the force due to gravity. So in reality though, on Earth, because there is an atmosphere, there's air, then whenever things move through the air, there is going to be air resistance acting on them. However, quite often the effect of that is so small that like it may as well not be there. Something would have to be either moving really fast for air resistance to be significant, or it would need to have a really big area. That's a slight spoiler for what we're about to talk about, but it would need to have a big area, because then you're like having to move a lot of air out of the way, right? I'm getting slightly ahead of myself, bit rambly, sorry. What was I saying? So something's in free fall if the only force acting on it is its weight. Okay, now if that is the case, then we notice something quite interesting, and the reason I did go off on that slight tangent there is because quite often it is actually the case. And if I was to stand here and drop something onto the floor, because it's not falling that far, and the object doesn't have time really to speed up that much, then air resistance won't have much of an effect, and that's why this wee demonstration is quite cool. I can't demonstrate for you now. One, I don't want to wreck my floors, and two, I don't really have anything that I could do it with. But whenever we are in school, I would always take, you know, those wee masses that we use in experiments. I would always have like a 100 gram mass here and a 500 gram mass here, like just 5 of the 100s taped together, and drop them onto the floor. So the most frequent mistake that people make is that they think the 500 gram one is going to fall and hit the ground first, but they both hit the ground at the same time, and that's because they're both accelerating towards the ground at the same rate. If you think back to those equations of motion, like they both have the same starting velocity, they both have the same acceleration of 10, they're both falling the same distance, so the time taken to reach the floor is going to be the same. Yeah, if we were to use like S equals ut plus a half at squared, or v equals u plus at, they're both going to hit the ground at the same time, because nowhere in those equations of motion does the mass or the weight come into it. So what we find is that weight has absolutely no impact on how fast something accelerates down towards the ground. So let's write that in here. So weight had no effect on the rate of acceleration when the objects fell. Heavier weights are going to hit the ground at the same time as lighter ones. If you have two objects which are very similar in nature to each other, and by that I mean like the size of them, I wouldn't like choose this and a feather, right? That's not going to work. Then go outside and give it a go, and you will see that they both do hit the ground at the same time. Now, once we had done that in school, then I would go on and I would do a similar experiment, but with like a sheet of paper like this and a scrunched up bit of paper. And the whole point of that was so that you would see that the scrunched up bit of paper would fall like relatively quickly, and the sheet of paper should float down nice and slowly. Now, the difference between those two, and why even though they're the same mass, they have the same weight, it's one sheet of paper each, the reason why those two hit the ground at different, or accelerate at different rates, is because on the sheet of paper, because it is a big flat area, then it's a big area, and air resistance does have an effect, because all air resistance is you, like the object having to like shove the air particles out of the way as it moves through the air. Okay, so with the scrunched up bit of paper, it's not having to push that much out of the way, it's really compactly tight, packed together, whereas the flat bit of paper, it has a big area, and it's having to move all that air out of the way, so that's why it sort of floats down really slowly. So I'm going to write that down here for you. So the shape and size of the object did affect. Now, I mess up affect and effect all the time. I initially wrote affect, but I think this one's actually effect. Correct me if I'm wrong, you'll be better at that than me. So that, I tried to change it to an E, it didn't work. So the shape and size of an object did affect the rate of acceleration. This is because of how different sized objects are affected by air resistance. Now, what we will find is that quite often physics questions neglect air resistance. So they'll say air resistance is negligible, which means that it's so small that you just ignore it. It doesn't have a big enough effect to take it into account. Or they'll say air resistance is ignored. So that just means that for that question, everything's accelerating down towards the ground at the same rate. So over to 200, that's just what this is saying here. In the absence of air resistance, all bodies accelerate towards the ground at the same rate. This rate is called acceleration of free fall, g, and it's 10 meters per second squared near the surface of the Earth. So what does this actually mean? It means that a falling object's speed will increase by 10 meters per second every second as it falls. So this is asking us to sketch a velocity time graph and a displacement time graph for an object in free fall. Now, this is putting into use what we have already learnt about our graphs, our motion graphs, so the last three topic there. So let's think it through. First of all, it's asking us to do a velocity time graph. Okay. Let me see, it means the falling object speed will increase by 10 meters per second every second as it falls. It's falling at a rate of 10 meters per second squared, or sorry, it's accelerating at a rate of 10 meters per second squared. So that means every second its speed increases by the same amount. So that means, I should really use a ruler here, look at the heck of that. That means that you're going to get a nice straight line graph because its speed is increasing, but it's doing so at a uniform rate or a linear rate. So every second the velocity increases by the same amount. The next one then it had asked us to do was a displacement time graph. So I'm not putting an S there just in case we think that's speed, so just do disp for displacement. Now, with the displacement time graph, do you remember the gradient of the graph tells you the velocity? Well, we know the velocity is increasing, so that means this graph is going to be getting steeper and steeper and steeper. So it ends up actually being a curve like that. So we talked about this whenever we were doing our motion topic. So at the start, it starts off quite slow. So for every second that's going past, its displacement isn't increasing that much, but as it speeds up, then it gets steeper and steeper. So in the same amount of time here, like the last second, its speed, or sorry, it has travelled a much bigger distance because its speed has increased so much. So down here, can you figure out why all objects accelerate towards the ground at the same rate? And it's we did this yesterday. It's telling us think about Newton's second law and or the weight equation. So this is just linking these two here. We'll write this in. Okay, so just showing that the two equations are like directly related, that W equals mg is really just a special case of F equals ma. So everything accelerates at a constant rate due to gravity. Get that written in, thank you very much. So carrying on here on page 201, this is the stuff I have been blethering about, so I'm going to try and not ramble too much here. But how come absolutely everything doesn't actually accelerate to the ground at the same rate then? It's because of air resistance. So in the Earth's atmosphere, air resistance does act on falling bodies. It can only be ignored if the force it exerts is very, very small. So something like dropping my pen onto the table is going to be like minimal. You're not going to notice it. Hope that didn't make a big massive noise, sorry if it did. In the Earth's atmosphere, air resistance does act on falling bodies. It can only be ignored if it's really, really small. So the force exerted by air resistance is affected by a number of factors. So we've talked about that already. First of all, area. So the bigger the surface area of an object, the bigger the air resistance. And remember I was saying there, that's just because literally it has more air to shove out of the way. So a tiny streamlined object is going to not have to push very much out of its way to slither its way down through the air, whereas a big clunky object has to shove everything out of its way. So the bigger the surface area of an object, the bigger the air resistance. And then the other one is speed. As speed increases, air resistance increases. Now I don't think I've talked about this one yet. So again, if we think about the pen going through the air, whenever it's going really slowly, every second it's not meeting that many air particles. So air resistance is going to be tiny. It doesn't have that many air particles to shove out of its way. Whereas whenever it's going really fast, it has way more air particles to shove out of the way every second. So that means the size of the air resistance force is much bigger, and you can feel it. Do it with me, right? So if you just move your hand really slowly, you don't really feel the air, whereas if you shove it backwards and forwards really quickly, you can feel the air. So you're feeling the air resistance there, and it's because every fraction of a second you're hitting way more air particles whenever you move faster than whenever you move slower. Promise me you'll try that out, and hopefully you'll understand it a wee bit better. Now, one of the very specific cases that can get asked about is a parachutist jumping out of its like plane or whatever they jump out of, right? And this here is actually literally the exact same as your notes from year 9. So instead of making you write it all out, I have it written in already. I hope it's photocopied all right. But both of these factors, the area and the speed, are demonstrated when a skydiver falls from the instant they jump until they land. So whenever they first jump out of the plane, like this split second that they jump out of there, the only force acting is weight. So the resultant force is going to be their weight. So whenever they first jump out, their acceleration is literally just going to be acceleration due to gravity, so 10 meters per second squared. Then, as they start to fall, air resistance does start to act because they're moving through the air. So that's this next one. You can see here, it hasn't really photocopied that way. We've got weight acting down the way, and then we'll have air resistance acting up the way. But do you see how the weight is bigger than the air resistance? Well, that means that the resultant force is still going down the way. So they are still accelerating down the way. So, but as she gets faster, she hits more air particles each second. The more air particles she hits, the greater the air resistance. So this stops her increasing speed as quickly. So let's think that through again. First jump out, the only force acting is weight. We've got a big acceleration down the way. As soon as she starts to fall, she starts to hit more air particles, and as she's speeding up, she's hitting more and more and more air particles every second. So that means that the air resistance is getting bigger and bigger. So the size of the forces, this one here, is going to be getting bigger and bigger and bigger and bigger and bigger. Eventually, we're going to reach the stage where it's equal to weight. And Newton's first law, if the forces are balanced, what's it going to be doing? Traveling at a constant velocity, isn't it? Let's turn over. So eventually she'll reach a speed where she's going fast enough that air resistance is going to be equal to her weight, and then she reaches that constant velocity, which can be called terminal velocity or terminal speed. So when the upwards force of air resistance equals the weight of the parachutist, the forces on her are balanced, so she travels at a constant speed, terminal speed. Velocity is probably a little bit better to say there. Now, as soon as she opens her parachute, then that increases the area massively. So that's going to be a big increase in air resistance, which now means that the upwards force is bigger than the downwards force. So it's going to cause a really big deceleration. Now, she's still moving down the way, but because she's moving down the way and the resultant force is up the way, that's why she starts to slow down. Okay, because it's like all those questions with the car crash. I don't know why physics questions always have car crashes in it, but the person's moving forward and the force is going in the opposite direction. Okay, so when the parachute opens, the parachute hits lots of air particles. The upwards force of air resistance increases, so she slows down. So it's because air resistance is now bigger than weight. Last wee one then. Eventually those forces are going to balance each other out again and she'll reach a new terminal speed. Let's read it. So the air resistance is much larger with the parachute open. After a while, air resistance equals her weight again at a much lower speed. The forces are balanced. She falls at a lower terminal speed and lands safely. So what we're going to finish off with today is doing this speed time graph for a skydiver. So we're going to be taking all of this information, like from all of these stages of the skydive, and putting it on a graph. Okay, and whenever we're doing that, we'll talk through it again because I don't know how clear I was with that. Right, so page 203, turn it sideways for me, and let's get this graph drawn. I tell you what, we'll sketch the graph first of all, then we will talk through it while like writing some notes on it. So let's get this drawn down. So this is the shape of our graph. So straight line here, but then starting to curve off and then reaching that constant speed or terminal velocity. And then a big dramatic decrease in speed. That's whenever the parachute opens. Then reaching another terminal velocity and then down hitting the ground. Okay. So I'm going to label a few different points here. Okay. So I'm going to call that A, B. That really, I'm trying to indicate that as like the point where my graph has gone from a straight line until it's starting to curve round. C will be here, D will be here, E, F, G. And then we're going to use those letters in our description, just in case you're like, why is she writing that on? So A to B is just that initial acceleration. So in this little section here, we have our person, right? We've got a big weight force acting down the way, but at this stage air resistance is quite small. So because weight is greater than air resistance, the resultant force is downwards, so it's accelerating downwards. So resultant force downwards, so acceleration downwards. Okay, now from B to C then, as the speed increases, the air resistance is going to increase. So that means that this, oh, I put AB there instead of AR. Hold on, let me fix that. Better, right? So as the speed increases, the air resistance is going to increase, which means the size of this upward force increases. So it's not quite as big as weight yet, but it's bigger than it was here. Okay, so let's write that in for this little section. I'll draw my wee person here, otherwise I'm going to run out of room. So here's my wee person. I'm going to try and get that weight looking the same as I did before. About the same. And my air resistance, I'm going to draw it a bit bigger than it was before, but not as big as the weight. Is that obvious enough? Maybe a wee bit bigger than that. Okay, hopefully you get what I'm trying to do here with the different sizes. So air resistance increases as the speed increases. My wee arrows I'm just using for increases. So resultant force, which is downwards, decreases, because like now we've got this, which is the same as before. Never really even labelled these, look, but we're taking away a bigger force from it, so our resultant force is going to be less. So the why did I write as? Hold on. Do you see why quite often I pause the recording for writing down? I make mistakes all the time. Right, anyway, I'm going to read through this again. So at this stage here, because she's sped up, air resistance has increased. So that means the size of the resultant force, which is acting down the way, has decreased. So the acceleration decreases, which is why this line is getting less steep. Okay, so from C to D then, let's draw our little person. So this time air resistance and weight are now equal to each other. So it's just like a continuation on of this. As she speeds up, air resistance keeps increasing. So the resultant force keeps decreasing and decreasing and decreasing until eventually the air resistance is equal to weight. The resultant force is 0, so she travels at a constant speed. So we're going to write that in up here. So eventually air resistance increases so much that it is now equal to weight. There's no resultant force, so she travels, or he, at a constant velocity, or that could be speed, so constant velocity or speed there, which we call terminal velocity or speed. Okay, force is balanced, constant speed. Now, here is where the parachute opens. So add that in for me. Then, because the parachute has opened, that has increased the effect of air resistance dramatically. So now the air resistance force is massive compared to the weight. So she's going to decelerate because she's moving down, but the resultant force is going to be up the way. So I'm going to get that written and drawn in here. So here's my picture for this wee one. We've got a really big air resistance force compared to the weight, which I've tried to draw the same the whole way through. Don't know how successful that has been. And then this is just the wee description. So the parachute opened at D, so air resistance increases a lot. The resultant force is now up the way, so she decelerates. I should have said here, say if you don't like my wee arrow way for using arrows for increasing and decreasing, write the words in. Okay, there's no point writing it down if you don't understand it. It's just my wee system. Okay, eventually then the air resistance and weight are going to equal each other again, because I know the air resistance increased a lot here because of her opening up her parachute, but because she's slowed down, then that's going to have decreased it again. So it's increased because of the big area, but she slows down, So because of that slowing down, it's like the opposite effect of what's happening here. It means that the size of the air resistance is going to go back down again, and eventually it will be equal to weight. So we're at another new constant velocity. Okay, so here we go. Weight and air resistance about the same size as each other. So air resistance equals weight, constant velocity again. And then from F to G is like literally hitting the ground and decelerating to 0 on hitting the ground. So let's get that in as well. Okay, so there we go. Decelerates to 0 when they hit the ground. So that is it for today. Randomly, the last little bit in this section before we go on to applications of forces is like sort of back to the motion topic. So it's talking about the vertical motion under gravity. I'm going to leave that for next lesson. And then that's this topic done. Okay, it'll do us no harm to have a look back through whatchamacallit, those like the vertical motion under gravity stuff, because it is something that we all find difficult. Okay, so that is us for today. I'm going to ask you to show me your notes filled in. They should match mine. Make sure you've written everything that I've written down, and I will see you next day. Bye.